So in the last section, we looked at the connectivity between the different anatomical components of the hippocampus. So now we'll have a look at the connectivity on the individual neuron level. And typical pyramidal neurons in CA1 and CA3 are illustrated here. And on the right, the different layers in the CA fields are labeled as they're conventionally identified. These include the three layers I mentioned earlier: the pyramidal layer that contains somas, the Oriens layer that contains axons plus the basal dendrites of the pyramidals, and the radiatum layer that contains the apical dendrites. And three additional layers are commonly distinguished. There's a lacunosa moleculare layer that contains the tips of the apical dendrites. There's the alveus, which contains axons destined for a range of subcortical targets, such as the basal nuclei and the hypothalamus. Then there's the lucidum layer that carries the mossy fiber axons from the dentate gyrus to CA3, and this layer isn't there in CA1 or CA2. And inputs from different sources are physically segregated. In CA3 pyramidals, inputs from the entorhinal cortex arrive on the tips of the apical dendrites. Inputs from nearby CA3 pyramidals arrive on the main part of the apical dendrites. Inputs from more distant CA3 pyramidals arrive on the basal dendrites. Inputs from the dentate gyrus granule cells arrive on the most proximal part of the apical dendrites, the parts that are close to the soma. An analogous but simpler pattern is seen in CA1. Inputs from the entorhinal cortex arrive on the tufts of the apical dendrites. Inputs from CA3 and CA2 arrive on the main parts of the apical dendrites and on the basal dendrites. This segregation obviously has significant implications for how information derived from different sources is integrated by the neuron. So this is a summary of the hippocampal connectivity we've discussed so far. From the cortex, through the entorhinal cortex to the hippocampus proper, lots of feedback loops within the dentate gyrus and CA3, then information flow back through CA1 and out through the subicular complex to the entorhinal cortex and back to the cortex again. But in addition, there's also some major subcortical connectivity that can be viewed as part of the hippocampal system. First, there's strong connectivity from the CA fields to the septal nuclei in the basal forebrain, and reciprocal connectivity back from the septal nuclei. And this connectivity passes over the fornix nerve bundle, as we discussed earlier in the course. Secondly, there's strong connectivity from the subicular complex to the mammillary bodies in the hypothalamus, but the return connectivity targets CA2 and the dentate gyrus, and again, a lot of this passes over the fornix. Then there's connectivity from the subicular complex to the anterior thalamic nucleus, one of the nuclei of the thalamus that we'll get to later, and from the anterior thalamus back to the subicular complex. But also going from the anterior thalamus back to CA1 and to layers 5, 6 of the entorhinal cortex as well. The anterior thalamus gets quite a lot of its information from the hippocampus via the hypothalamus. Finally, there's also connectivity from the subicular complex and deep layers of the entorhinal cortex to the amygdala, and from the amygdala back to the subicular complex and to layer 3 of the entorhinal cortex. So the hippocampal system as a whole is made up of components located in many of the major anatomical structures. And apart from this pattern of connectivity, a major reason for viewing this as a single system is that damage to any part of the system tends to result in similar cognitive deficits, as we'll get to in the next section.